All right, welcome. Today, we're cracking open the Advanced Toolkit for software testing. We're going to cover 3 really powerful techniques for finding the kind of nasty bugs that hide deep inside your code, the kind that simple checks just won't catch. Okay, let's just dive right into the heart of the problem. This is a question every single developer has to wrestle with. Your program compiles, it runs, it doesn't crash. Awesome, right? But how do you know the answer it's giving you is actually correct? That, my friends, is a whole different ballgame.
And that's where this idea comes in. You can't just look at what comes out at the end. You've got to pop the hood, look inside, and really understand the structure of the code itself. This is the whole idea behind structural testing, and we're going to explore 3 advanced ways to do it.
Okay, first up, let's talk about becoming a data detective. I want you to imagine tracking a package, right? From the second it leaves the warehouse all the way to your front door. Well, data flow testing is pretty much that, but for the variables floating around inside your program.
So what this method does is it looks at the entire life of a variable. It starts from the moment it gets its value. We call that its definition. And it follows it all the way to every single point where that value gets used. And just to be super clear, this has absolutely nothing to do with those data flow diagrams you might be thinking of. Nope, this is all about the actual path data takes as your code runs. And this is exactly why it's such a game changer. It's brilliant at catching these super common but incredibly dangerous issues. I mean, on one side, you've got a variable that's defined but never used. That's just dead code, maybe some wasted memory. But on the other side, a variable that's used before it's ever been defined? Yikes. Your program is trying to use a value that's, well, who knows what it is. That can lead to some seriously weird, unpredictable bugs or just crash the whole thing. The beauty of this is how methodical it is. So first, you actually map out your code into a graph, so you can see every possible path it could take. Then, you go through and you pinpoint every single time a variable gets a value, the definitions, and every time it's used. And the last step? You create tests to cover all those crucial definition use paths. Basically, you test every possible journey that value can take from its creation to its use. All right, that's great for smaller stuff. But what about modern software? We're talking millions of lines of code. You can't just test the whole thing at once. You need a way to zoom in, to focus. And that's a huge challenge, right? Trying to follow one little variable through thousands or even millions of lines of code? It feels impossible. It's like trying to find one specific needle in a giant stack of other needles. And that's where program slicing is an absolute lifesaver. Think of it like a super smart magnifying glass for your code. You tell it, hey, I care about this variable right here on this line of code, and poof, it automatically pulls out only the lines of code that could ever affect that variable's value. It gives you a much smaller, focused slice to work with.
Let's make this real with a super simple example. We've got a few variables here. Okay, so let's say a bug report comes in, and we think the value of C is wrong. Specifically, we only care about what's happening to C right there on line 5. And here we go. This is a perfect illustration of a slice. You see, to figure out the value of C on line 5, what do we actually need? Well, we need line 1 where A is defined, and line 2 where B is defined. That's it. The calculation for D on line 4? Totally irrelevant. Even the old value of C on line 3 doesn't matter for our specific problem. The slice lets us just ignore all that noise, making our job way, way easier. Okay, so we've used these cool techniques, we've written a bunch of tests, we've built up this whole test suite, but that brings up a really interesting kind of meta question. How do we know our tests are any good? And this is a huge deal for anyone who's serious about software quality. Think about it. A test suite that always passes might just be a bad test suite. It gives you this false sense of security. It's like having a guard dog that's always asleep. You think you're safe, but you're totally exposed. And this brings us to our third tool, mutation testing. The idea here is just genius, really. To see how good your tests are, you intentionally break your code in small ways. You create these slightly faulty versions called mutants, and then you unleash your test suite on them to see if it can spot the problems. The process itself is pretty straightforward. So a tool will automatically go through your code and create tons of these mutants by making tiny changes, flipping a greater than to a less than, or a plus to a minus. Then you run your whole test suite against every single one of those broken versions. If one of your tests fails, that's a good thing. It means your test caught the bug, and we say the mutant has been killed.
Let's see what a kill looks like in practice. So, in our original program, we have a simple check, if A is greater than B. But our mutant, M1, changed that to if A equals B. Now, we run a test case where we know what should happen. We set A to 10 and B to 5. The original code passes, no problem. But the mutant? It gives the wrong answer, which causes our test to fail. And that's a win. We've killed the mutant, which proves this test case is actually useful.
And all of this boils down to one simple, powerful number, the mutation score. It's just the percentage of mutants that your test suite was able to kill. If you have a high score, let's say over 80%, you can be pretty confident that your tests are actually doing their job and can find real bugs when they pop up. All right, let's wrap this up and see how all three of these tools fit together in our Bug Hunters Toolkit. So, here's the main takeaway. These three techniques aren't competitors, they're collaborators. They each have a different job. You'll use data flow testing when you're really worried about how data is being handled. You'll pull out program slicing when you're deep in a massive code base trying to hunt down one specific bug. And you'll use mutation testing when you need to be absolutely sure your entire safety net of tests is actually strong enough.
And look, this stuff isn't just academic theory. Why does it really matter? Because better testing, more thoughtful testing, leads to better software for all of us. We're talking about software that's safer, more secure, and just flat out more reliable, whether it's the app on your phone or the massive systems that run, everything.
And that brings me to one final thought to leave you with. We're heading towards a future where AI is going to write more and more of our code. So if an AI writes the code, and maybe another AI writes the tests for that code, who tests the testers? Or what tests the testers? Suddenly, techniques like mutation testing, which are designed to check the quality of our checks, they're not just going to be helpful, they're going to be absolutely essential.